Welcome back to the deep dive. Today we are wrestling with something that feels like it should be the simplest concept in human history,
Right.
but somehow it manages to be the most complicated puzzle in the universe. We're talking about numbers,
Specifically, prime numbers.
specifically that strange, stubborn sequence that starts 2, 3, 5, 7, and just keeps marching on into infinity.
It really does. And I know for a lot of people, that phrase just brings up, bad memories of school worksheets.
Oh, absolutely. Finding the least common denominator.
Exactly. But before you tune out, you have to understand this isn't about doing mental math. This is about the fundamental atoms of the mathematical universe. We're looking at, well, the bedrock of reality.
That analogy, atoms, is exactly why I'm so excited about this one. We have a great stack of sources today. We're pulling from some heavy academic insights from T. Graz,
Uh-huh.
specifically a mathematician, Christian Elschultz, who has this really mischievous sense of humor we'll get to.
Oh, I'm looking forward to that.
We've also got the encyclopedic history from Wikipedia, to keep us grounded. And we're weaving in the narrative from Marcus Dusarto's book, The Music of the Primes.
Kusatoy is fantastic because he frames this whole thing not as a dry calculation, but as a hunt for harmony. It's almost musical.
It is. But I have to admit, the thing I'm most looking forward to is this sledgehammer joke.
From Eltholz, right?
Yeah. The idea that you can use the most complex math in history to prove something totally obvious, it just cracks me up.
It's a classic example of how mathematicians think. It's playful, but we have a lot of ground to cover before we get to the punchline.
We do. So the mission for this deep dive is to figure out why a simple list of numbers has captivated thinkers for over 2,000 years, why it protects your credit card, and this is the weirdest part, why it dictates the life cycles of insects.
It really is a search for order within what looks like, well, total chaos.
Let's start at ground zero. Let's unpack the definition. What actually makes a number prime?
So if we look at the definition, it's actually very strict. A prime number is a natural number greater than 1
Okay, greater than 1.
that is not a product of two smaller natural numbers.
Okay, so essentially it's a number that is unbreakable.
Precisely. Think of a number like 6. You can break 6 down, right? It's a 2 times 3.
Right.
Because it can be deconstructed, we call that a composite number. It's composed of other things. But take the number 5.
Uh-huh.
The only way to write it as a product is 1 times 5. There are no smaller building blocks. It just stands alone.
And this brings us back to that quote from Christian Elschultz at TU Graz. He says, prime numbers are like atoms.
All other numbers consist of them, but they themselves can't be divided any further. It's a perfect analogy.
It really is.
It works exactly like chemistry. You take a complex molecule, say water, and you break it down into hydrogen and oxygen. Those are the atoms. You can't break hydrogen down any further.
Right.
In math, you can take any number, no matter how huge, and break it down into a unique string of primes multiplied together.
So 12 isn't just 12. It's 2 times 2 times 3.
Right. And you can't go any further. The primes are the elemental table of mathematics.
But here's where I always get tripped up. You mentioned the definition says greater than 1. Why isn't 1 a prime number? It feels like it fits.
It does feel like it should.
Yeah. You can't divide it by anything but itself. It seems like the ultimate atom.
This was a debate that actually raged for centuries. If you look at the history, the early Greeks didn't even consider 1 to be a number at all.
Really?
To them, 1 was the unit. It was the generator of numbers, but not a number itself.
That's a very philosophical stance, like I am the alpha sort of thing.
Very. But then later, you had mathematicians like Christian Goldbach, and he was writing to Euler in the 1700s, listing 1 as a prime. So it wasn't always kicked out of the club.
So what changed? Why did we boot it out?
It all comes down to housekeeping, really. There's this rule called the fundamental theorem of arithmetic.
Sounds intimidating.
It sounds it, but it's beautiful. It just says that every number has unique prime factorization, a unique fingerprint.
Okay, a unique fingerprint. Walk me through that.
Take 6 again. Its fingerprint is 2 by 3. That is the only way to make 6 using primes.
Right.
But if we allowed 1 to be a prime, that uniqueness just vanishes.
Oh, because you could say 6 is 2 by 3 by 1.
Or 2 by 3 by 1 by 1. Or add another times 1 and another. You could do it forever. There would be infinite ways to describe the number 6.
Ah, I get it. The chemistry breaks down. It would be like saying water is H2O.
Yeah.
Plus an infinite number of ghosts.
Exactly. You lose all the precision. So to keep that theorem solid, mathematicians just agreed. 1 is not prime.
Poor number 1. Excluded just to keep the filing system tidy.
I know. But everyone else has their favorites. Elsholtz, from our source, says his favorite prime is 17.
A solid choice. But the real problem isn't identifying them one by one. It's finding out where they are hiding. When you look at a number line, they don't seem to follow any kind of schedule.
And that is the core problem. That is the thing that keeps mathematicians up at night. If you count by twos, you know exactly where the next number is. 2, 4, 6, 8. Predictable.
Of course.
But primes, you have 2, 3, 5, 7. Then a gap, 11, 13. A bigger gap, 17, 19. They just pop up erratically.
It looks like noise, like static on a radio.
It does. And yet, we suspect there's a pattern. And this brings us to one of the best stories in our stack, the Ulam spiral.
I love this story because it proves that boredom is the mother of invention.
It really is. So this goes back to 1963. Stanislaw Ulam, brilliant mathematician, worked on the Manhattan Project, but he was sitting in a scientific meeting,
Okay.
listening to, in his words, a long and very boring paper.
We have all been there, staring at the notepad, zone out time.
Exactly. So he just starts doodling. He wrote the number 1 in the center of the page, then started writing integers spiraling outward. 2, 3, 4, 5.
Just killing time, making a little number maze.
Right. But then, for some reason, maybe intuition, maybe just messing around, he decided to circle only the prime numbers.
And what did he see?
He saw something that shouldn't have been there. The primes weren't just scattered like dust. They were lining up.
What?
They formed distinct diagonal lines.
Yeah.
Even some horizontal and vertical lines. In this sea of chaos, a visual structure emerged.
That is wild, just by arranging them in a spiral.
Yes, and it wasn't just a doodle. He later used the Maniac 6 computer at Los Alamos to generate a massive version, and the pattern held. It was visual proof that there is some kind of hidden order.
It's like finding a secret code in the static.
That's a great way to put it. And that tension between randomness and a hidden pattern is what Marcus du Sautoy captures so well in the music of the primes.
I really liked his metaphor of music. It
Yeah.
makes the math feel less rigid.
It transforms the problem. Instead of looking at primes as just individual rocks, he asks us to listen for their rhythm, to find the harmony.
And the conductor of this orchestra, according to our sources, is Bernhard Riemann.
Riemann is the giant here.
Mm-hmm.
Mid-19th century, he looks at this problem and proposes what we now call the Riemann hypothesis.
Yep.
He constructed this mathematical landscape, the zeta function.
And without getting too bogged down in the calculus, how should we picture this landscape?
Imagine a 3D terrain with hills and valleys. Riemann predicted that the zeros of this function, think of them as the points where the landscape dips down to exactly sea level.
Okay, the sea level point.
Those points control exactly how the primes are distributed.
So if you know where the sea level points are, you know where the primes are.
Essentially, yes. And his hypothesis is that all these significant zeros line up perfectly on a single straight line, the critical line.
And if that's true,
The primes are orderly. There is a system.
and if it's false, if one of those zeros is just a little bit off the line,
Then the music becomes noise. The primes really are random. And our understanding of number theory has a massive crack in its foundation.
and the stakes here are incredibly high. We're not just talking academic glory, we're talking literal cash.
Serious cash. The Clay Mathematics Institute listed this as one of their millennium problems. If you can prove it or disprove it, you win $1 million.
Right? $1 million? Is it just because it's hard?
It's because so much of modern mathematics is built on the assumption that it is true. There are thousands of theorems that start with the phrase, assuming the Riemann hypothesis is true.
No way.
If someone proved it false, a huge chunk of mathematical knowledge would just collapse.
So it's a load-bearing wall for the entire field.
Exactly. It's holding up the roof.
Speaking of proving things, I want to pivot back to Christian Elsholtz at TU Graz, because he did something recently that plays with this idea of proofs. It's this mathematical joke.
Ah, yes, the sledgehammer. This is such a wonderful glimpse into how mathematicians have fun.
Okay, lay it out for us. What did he actually do?
So, you have to understand the two players here. First, Euclid's theorem. This is the proof that there are an infinite number of primes. We've known this since 300 BC. It's ancient, it's elegant.
Okay, so that's the nut, the easy thing to crack.
Right. Then you have Fermat's last theorem. This thing was a notorious beast. It wasn't proven until the 1990s by Andrew Wiles. And the proof is hundreds of pages of the most complex, cutting-edge math you can imagine.
So one is a tricycle and the other is a space shuttle.
Perfect analogy. And Elsholtz decided to prove the tricycle exists by using the space shuttle.
That is ridiculous. Why would you do that?
For the sheer joy of it,
Yeah.
he literally called it using a sledgehammer to crack a nut.
So how does the logic even work?
It's a proof by contradiction. He imagined a world where Euclid was wrong, where there is a finite list of primes. He then showed that if that were true, it would create a contradiction that breaks Fermat's last theorem.
So he's saying if primes run out, then this super fancy math by Andrew Wiles stops working.
Exactly. And since we know Wiles is right, Euclid must also be right.
I love that. It's totally unnecessary, but it highlights how connected everything is.
It highlights the playfulness of the field.
Yeah.
And it was published in a serious journal because it shows these deep structural links between concepts that seem miles apart.
So we have ancient Greeks, million-dollar prizes, sledgehammer jokes, but I can hear the listener asking, why does this matter to me?
Well, do you use the internet?
Every single day.
Then you care about primes because they are the lock on your digital front door.
This is cryptography.
Specifically, public key cryptography, or RSA.
Oh.
This system changed everything in the 1970s. Before this, primes were thought to be just pure math.
With no application.
None. Now they're the foundation of global commerce.
So break that down. How do prime numbers keep my email safe?
It relies on a very simple asymmetry. It is incredibly easy to take two massive prime numbers and multiply them together. A computer can do that in a split second.
Okay, that's the easy direction, like mixing blue and yellow paint to get green.
That is a perfect analogy. Easy to mix the paint. But if I give you the pot of green paint and ask you to separate it back into the exact shades of blue and yellow that created it?
That's incredibly hard. Maybe impossible.
Right. In math terms, factoring that big number back into its original primes would take supercomputers millions of years. The security of the whole system relies on that difficulty.
So if someone solved that Riemann hypothesis,
If they found a shortcut to the primes, it's possible they could unmix the paint. They could potentially break the encryption that secures the world's data.
that is terrifying. So the chaos of the primes is actually what keeps us safe.
In a sense, yes. We rely on their complexity to hide our secrets.
But it's not just computers. You mentioned biology earlier. This blew my mind. The cicadas.
The magicicated genus. This is one of nature's greatest mathematical wonders.
These are the bugs that live underground for years and then all come out at once, right?
Yes, they spend almost their entire lives as nymphs underground. But they don't stay down for a random amount of time. They stay down for exactly 13 years, or exactly 17 years.
And those are both prime numbers. That can't be a coincidence.
It definitely isn't. Biologists have a very compelling theory for why.
What's the strategy? Why not 12 years? Or 15?
Okay, so imagine you are a predator that eats cicadas. And let's say your population booms in cycles maybe every 2 years or every 4 years.
Okay, so I'm a bird, and every 4 years, there are a lot of me.
If the cicadas emerged every 12 years, that would be a disaster for them. 12 is divisible by 2, 3, 4, and 6. Any predator on a 2, 3, or 4-year cycle would be waiting for them. The cycles would sync up.
He's got too many factors, too many open doors for predators.
Exactly. But 13, or 17. A predator with a 2-year cycle will only meet a 17-year cicada every 34 years. A 3-year predator only needs them every 51 years.
Wow. So by choosing a prime number, they are maximizing the gap between feasts.
Precisely. They minimize the chance of synchronizing with a predator. It's evolutionary number theory.
That is incredible. Biology found them before we did.
Which is probably why they show up in our culture, too. I mean, Carl Sagan used them in Contact.
Right. When the aliens send the signal, they don't send English. They send pulses of prime numbers.
Yeah.
2.3, 5.7.
Because math is the universal language. And primes are the most fundamental, non-natural signal you could send.
And you see it in the curious incident of the dog in the nighttime, where the chapters are numbered with primes.
Which reflects the protagonist's need for order. 7 will always be prime, no matter what happens.
So we have gone from boring meetings with Ulam to high-stakes cryptography to insects hiding underground. It's amazing that these atoms of math govern so much.
It is, and the most exciting part is what we still don't know. We know they go on forever, but the pattern.
Yeah.
That is still just out of reach.
And that leads us to our final thought for you, the listener. Something to chew on.
We talked about how primes get rarer as you go higher. They get lonely. But there's this strange phenomenon called twin primes.
No.
These are pairs of primes that are just 2 numbers apart, like 3 and 5, or 17 and 19.
Neighbors.
Exactly. And as we look at massive numbers, we still find these pairs. But here is the thing. We don't know if they go on forever.
The twin prime conjecture.
That's it. We suspect that no matter how far you go, you will eventually find another pair of primes huddled together in the darkness. But we can't prove it. Even with all our computers, the gaps between the numbers remain a mystery.
So the next time you see a number on your credit card or a calendar, remember that hidden inside it are these ancient, unbreakable atoms.
And look for the patterns in the chaos. Because as Ulam showed us, sometimes the most profound discoveries happen when you're just doodling.
That's it for this deep dive. Thanks for listening.